Now, this correspondence in the energy levels and the classical frequencies is very useful to give us good intuitive understanding of how energy spectra behave. So I want to give you an example, a few examples actually, uses of the correspondence principle. It gives us really a way of having very good intuition of what these energy spectra look like for different systems, for different quantum systems, and we can anticipate how they behave simply by building on our knowledge of classical physics. And this will be a very important skill as we begin in our formal theory to solve for the energy levels of a variety of different systems. So the first use I want to show you is that it explains a somewhat mysterious phenomena that I like to call the energy compression in the hydrogen spectrum. So you will recall when we looked at the energy values in hydrogen, if this is 0, there's a lowest energy state of minus 13.65 electron volts, right? And then the next state is minus 1365 divided by 2 squared, or divided by 4, which would put it right about here. So this is minus 13.65 EV divided by 4. And then there's another one divided by 9, which is approximately 1/10 of this distance. So I don't know, it would be about here. And then divide by 16. You know, they get smaller and smaller and smaller. What you'll notice is that the energy levels get closer and closer together as the energy increases. Now, different energy spectra have different behaviors as you increase the energy, and we can actually understand this behavior very quickly from the correspondence principle. Here's the argument that I would use. Notice, as the energy of my system here goes upward, we know that the radii of the orbits will be getting larger, right? Because we're putting more energy into this orbital system that is going to be that will pull the electron further and further from its center of attraction. Now, as the radius goes up in an orbital problem, we know that the period of those far out orbits actually gets longer. We know this, for instance, from orbital motions. Jupiter has a period of about 12 years, is longer than the Earth year because it's further out from the sun. And of course, as the period increases, the frequency of the motion, the classical frequency, decreases. And that means then that the product of Planck's constant and that classical frequency, which we know must match the energy spacing in the spectrum, must be going down. So this simple correspondence argument, when you follow through the chain of logic, teaches you that increasing the energy in the system, we should expect to see the spacings to get closer and closer together, and that's exactly what they do. Now, what I would like to do with this next is to make a guess at the behavior we expect in a second system.